as we study addition reactions, there's another type of addition reaction that can happen other than just adding HBr and HCl all the time to an alkene. Alkenes can also react with the diatomic halogens like Cl2, Br2, etc. Let's take a look at how that occurs. Well, let's say that we have this example right here where we have an alkene and it's actually a 2-butene and it's reacting with Br2. Well, we can right away see that both of these Brs are pretty electronegative. So what can happen is this alkene, as it sort of runs into the Br here, this other Br is pulling so strongly that it's able to pull those electrons over, right? Now, I'm going to draw the transition state here because I think that's going to help us predict what else is going to go on here. So let's say that we're looking at this transition state, and we are currently forming a bond here to this Br. Now, at the same time, that Br is breaking a bond with this other Br. And this other Br is taking all of those electrons with it. So if you notice this, you're going, oh my goodness, this Br is quite negative because in the end, once it takes its electrons and leaves, it's essentially just going to be a Br with an octet, a bromide, which has a negative charge, right? So because we know that's happening, we know there's a partial negative charge there. Well, as that's occurring, remember that we also have something else going on here. We are breaking this alkene. As that alkene breaks, what's happening to the carbon that it's leaving? Well, of course, the carbon that it's leaving is turning into a carbocation in a way, right? It's losing those electrons and it's becoming positive. But as these other electrons here are attaching the Br, well, goodness, the Br has all these electrons. In fact, I'm even going to draw one of these pairs of electrons like this because has a lot of electron density there. Well, we notice this electron density here, and we notice there's a partial positive charge here. That's really interesting. So what's going to happen here is we're actually also going to take this negativity of that electron pair and we're going to combine it with this. Let me show you what this looks like. This actually looks like these electrons right here attacking. Now, where are they going to attack? Let's just draw the line right here. They're going to attack where the electrons are leaving. So these happen at the same time. The reason I have to draw these arrows at the same time is because as the alkene is breaking, it's forming a partial positive charge on the carbon that can be attacked by the bromine's electrons, right? What this ends up forming, I need to redraw our complex down here, but really what we're doing is a lot of complex stuff at this time. We're actually, as we're breaking that, we're forming a new bond with this Br from both of these carbons, right? And then we're breaking this Br away. And so that's basically what's going on here. In the end, what we're going to get as a result of this, I'll draw for you, and it is called a brominium ion. Now you hear the eum always like ammonium, right? Ammonium, hydronium, those are positive ions. And interestingly enough, what we're going to get here is a positive ion. We're going to get our Br and because our Br has two bonds, if you remember the trends I taught you a while ago, this Br is actually going to have a positive charge on it. Now remember that there were hydrogens of course, on this alkene. So we still have those hydrogens here, right? But that's what our brominium ion is going to look like. Now, if you look at what I've left up here, I left our bromide, right? Because that did break off here. This is really useful for us to remember, because after this first step, yes, when we broke that off, we do still have this Br bromide floating around here. Now, what is a negative Br going to do with this positive Br? Brominium. Well, remember, Br brominium is positive, but it's also very electronegative. So it's going to really pull on electrons from these two carbons, right? There's going to be a huge pull, and I'll draw a dipole here, and a huge pull here, right? So this thing is really pulling on those electrons. So what we have is actually an incredible partial positive charge at those carbons. This is a great opportunity for our bromide, which, by the way, to be accurate here, let's make it red, because our nucleophiles are red. And that Br is going to attack that partial positive carbon. At the same time, this Br is going to break one bond with that carbon. Now, bear in mind, this is what we call a backside attack. This is a backside attack on that carbon. Now, it's really important to review what a backside attack is. If we imagine there's this carbon here, it's forming a sigma bond with this Br, right? So this is like, let's draw it right here in blue. And it's got these little deals out here, right? This is our sigma bond. But what do we know is also there? Well, there has to be a, you all know what I'm drawing here, right? What does this look like? Yeah, that's a sigma star anti-bonding orbital, right? Now, are there any electrons in it? No, there are electrons in only the sigma orbital. By the way, just to make this kind of accurate, I'll put this up here because it's pretty high energy, right? So that anti-bonding orbital doesn't have any electrons in it. Well, this Br here, that's negative, has these electrons that it's able to flow into that anti-bonding orbital. As it flows into the anti-bonding orbital, it's able to break that bond with the other Br. Now, as it's breaking, because remember, we're creating a bond order here that's not favorable. As it breaks, what it ends up turning into here is a sigma or a bonding orbital for the Br and the carbon, right, as it breaks that. But notice that it's coming from the back side where that anti-bonding orbital is. Remember, the anti-bonding orbital is on the back side of that bond. That is why we call this a backside attack. Now, it's really important for our stereochemistry that we're going to go into a bit in a second. So if you look at this, we added the first Br on one side here, and the second Br we actually have coming right here with a backside attack. So this is what we call, in chemistry terms, and I'll do purple for stereochem, this is called an anti-addition. Remember, this is addition reaction, but why do I call it an anti-addition? Because the Brs in the end, if I look at our final result, so if we look at our final result, what we're going to have is one Br that's still here. As we drew it before, it's in the back, like this. And then, of course, we have our, we have our hydrogen here in the front. But the other Br, remember, had to attack from the opposite side. So since that Br was towards the back, that other Br came in the front. The second this red Br here came in on the opposite side. So what we have here is a Br and a hydrogen like this. So this is called anti-addition because those BRs have added to the opposite sides. Whenever we add it to the alkene, we're adding it to those opposite sides. So this will always be an anti-addition. Something else I want to address with this. Notice what we have for our result here. In fact, I understand that this is a meso compound, right? Could be a meso compound. I'll let you answer whether or not it's a meso compound. But I will also show you another important thing that played into this. Here we had a trans alkene. Would that trans alkene produce a meso compound? What if that alkene was cis? Would that change any of this? I'll let you draw out the reaction and answer those questions. I'll give you a hint. Either cis or trans, one of them will make a meso compound. The other will not. So it's something to bear in mind here. One last addition that we can do to this. This reaction would be if we threw an alkene with just Br2. But what if instead we threw in a Br2, but we did this in a solution of water? Well, what would happen here once we formed our brominium ion is we could have water backside attack. We could have bromine backside attack. But don't forget, we have another really good nucleophile around. We have water because it has these electrons hanging off on one side, a nice dipole for us to attack with. What this would lead to is the exact same anti-addition. However, the difference is that on one of these, we'd have a bromine from our first brominium ion. On the second one, we would have a protonated alcohol that we would add. Now, of course, this protonated alcohol wouldn't last for long because we have a lot of water floating around, and water is going to be our base. It's going to come along and deprotonate that alcohol for us, returning it to a nice product of a bromine and an alcohol, one on each side. We call this a halohydrin, right? Because we have water and we have a halogen. So this is called a halohydrin that we are going to form. So this is another example of what can happen with these anti-additions like this. And they always form because of that backside attack.